The next two modules deal with the chi-square statistic, which is one that deals with counts of nominal variables rather than the interval and ratio data that we have been dealing with. You're going to find that the concepts are much easier to understand and the calculations are much less complicated compared to the analysis of variance that we have been doing. And some of the results are even fun to look at. Let's dig in. All of our hypothesis tests up until this point have been what we call parametric, meaning that we were trying to estimate a population parameter, or the difference of two parameters, like two means. When we do those kinds of tests, we make a variety of assumptions, including that the distributions are normal, that the variance is equal between the groups, and that we have a numerical score for each individual, so that our data are interval or ratio. We usually need about 30 cases. If you think back to our central limit theorem, you remember that around 25 or 30 cases was the place where the distribution of sample means became relatively normal. These tests tend to be robust. In other words, they don't instantly fall apart when the assumptions are violated a little bit, but nonetheless they are completely unable to work when we have nominal data because you can't compute a mean or a variance for nominal data. Non-parametric tests are tests that don't have those assumptions. They're sometimes also called distribution-free because we're not concerned with having a normal distribution. In fact, nominal data can't have a normal distribution because they do not go from low to high. Parametric tests have greater power when they are appropriate to use, and we'll be studying power in an upcoming module. But the basic concept means that if there is a difference in the population, a powerful test is one that's able to detect even a subtle effect, whereas a test with less power is not able to detect it. Our non-parametric tests tend to have lower power, but they do let us study situations and types of data that otherwise would have to be passed over. So that's why we need to have both kinds of tests. We have two kinds of chi-square test, and the first one is the chi-square goodness of fit. It works on just one variable at a time and tries to see whether that variable has about the same proportions in a sample as in some population or else in a hypothesized value. So we're looking to see how well do the actual data fit a hypothesis that we made about those data. As you can tell, because we're speaking about proportions, we're dealing with nominal data, which are data that come in categories, things like eye color or college major or make of car. And sometimes we also use these chi-square tests when we're dealing with ordinal data, something that might go from low to high but not in equal intervals, like t-shirt sizes. So our chi-square goodness of fit test is going to compare the observed frequency count in a sample with the frequency count that we would expect if we presumed that the null hypothesis were true. And in order to do this test, we have to compute what the frequency count would be, what we would expect if that null hypothesis were true, and we call those the expected frequencies. And it's the one that we would predict from that null hypothesis. And it's sort of an ideal or a hypothetical sample to which we're comparing our actual sample. So the null hypothesis for our goodness of fit test specifies the proportion, or you could say the percentage of the sample that will fall into each category. And there are a couple of different rationales that are often used. One would just be to say that we predict that the sample distribution will have an equal number among all of the categories. So if we had 4 categories, there would just be 25% or 1/4 in each category. Another way of having the null hypothesis, and this is the one that matches the example in the textbook, is to presume that the group in a sample matches a larger population. In the example in the textbook, they're considering what would the distribution of people across political parties be in a small part of a county if we knew what the region-wide population distribution was. In other words, are the people in a city distributed politically the same way as the entire region? To illustrate these two ways of having a null hypothesis, I've put together a really simple idea that we often see on TV, where they have various kind of taste test. So if we were looking at an equal likelihood or a no preference version of the null hypothesis, and we had three types of soft drinks, cola, lemon lime, and something else, our null hypothesis would simply be that 1/3 of the group of the sample would want cola, 1/3 would want lemon lime, and 1/3 would want something else. So that's just saying that our null hypothesis is all of the groups are equally likely. Alternatively, we might have data about some large population. So for instance, we might know that in the United States, across the country, 50% of the people prefer cola, about 35% like lemon lime, and that the other 15% like other drinks. And so we might be asking, are the people in Duluth, Minnesota the same as the general population of the US? And if so, we would expect when we went out and got a sample of Duluthians that half of them would want cola, 35% would want lemon lime, and 15% would want something else. Then we could go and get our actual sample and see if it matched those proportions. So I could go out and get my actual sample. So these are my hypothetical Duluthians. And when I went and got my actual sample, I might find that out of 100 Duluthians, 60 of them, or 60%, liked cola, 30% liked lemon lime, and only 10% liked something else. So you can see that it's the same approximate distribution that the population had, more cola, some lemon lime, and a little bit of everything else, but it is not exactly the same. So our chi-square goodness of fit test is going to give us a way of saying, is this just the random chance variability that can happen when I draw a sample, or is there something here that makes me think that Duluth really does like cola at a higher rate than the U.S. population does as a whole? So we'll look at how we go about computing that statistic. So we're looking here at the equation for our chi-square statistic, and the first thing we need to do is to get comfortable with the various symbols and notations that are here. So our chi-square is the Greek letter chi. It looks kind of like an X, and we're talking about chi-squared. We never take the square root, so there never is such a thing as chi by itself. So we're looking at chi-square as the name of the statistic, and we're going to compute it by looking in the cells, the count of each category. And the first thing that we'll have is the observed frequency. In other words, in my sample, how many people do I actually count that liked cola, or that liked lemon lime, or that liked some other kind of beverage. So my observed frequency is the count in my actual sample. My expected frequency is one that I computed based on either that idea of equal groups, that all the groups would be equally likely, or based on some previous population. Before I actually carry out the test, I know what my expected proportions would be, and then I just have to apply them to the sample size. We'll be doing some of those computations in one of the other videos, so you'll be able to see it there. So the equation tells me that my chi-square statistic is a sum, remember our summation sign, in each cell or each category. I take the observed count and I subtract the expected count. And if you think about it, it means that if my null hypothesis is true, or very close to true, then the expected count and the observed count will be very close to each other, and I'll have a very small number in the numerator of this fraction here. And then I square it, and that is where the square comes into chi-square. So I say, here's the difference between what I got and what I expected. I've squared it, and then I divide it by what I expected. So the end result is that if my observed and expected were very close, I'd have something almost zero on the top over this expected value, and I add those values up for the total number of cells that I have, the number of categories. So if I have 3 soft drinks, I would compute the observed minus the expected, square it, and divide by the expected for cola. Then I'd do the same thing for lemon lime. Then I'd do the same thing for the category of other. And once I'd done it 3 times, once for each category, I'd add those values together, and the sum of all those values would be my chi-square statistic. So I end up with a single number. Just as we've had in all of our other statistical tests, the chi-square distribution is a curve, and we are basically defining our p-value, our probability of getting a particular chi-square, as the part in the right-hand tail, and there's some critical value of chi-square. It differs with the degrees of freedom. We'll look at those in just a minute. And that critical value cuts off an area that is the same as our alpha size. So if I'm looking at alpha of 0.05, it would mean that 5% of the area under the entire curve is out in the tail. When I'm working with computing by hand, I end up computing a chi-square statistic and looking up a critical value in a table. When I'm working with Excel, it will give me the p-value directly, and I don't need to look in the table at all. So when the null hypothesis is true, the chi-square values will be relatively small, and they'll be in this area that's consistent with the null hypothesis. But if my chi-square value is large, it means that the expected values were quite different from the observed values, and in that situation I would get a chi-square that fell into my rejection region. So in fact, our chi-square distribution is positively skewed, as you just saw, and it is a family of distributions, the same way that our F and our T distributions. They have the same shape, but it moves slightly to the right according to the degrees of freedom. In our goodness of fit test, we have degrees of freedom as C minus 1, where C is the number of categories. When we have 2 variables in our other test, our degrees of freedom will be slightly different, but it's still going to be quite easy to compute. So this picture lets you see how the different degrees of freedom change the shape of the chi-square distribution. When degrees of freedom are 1, which would mean we had exactly 2 categories in this goodness of fit situation, there's actually no upper humpy part of the curve at all. It just starts at a peak and comes down. As we have 2 or more degrees of freedom, the curve develops a curve, and as we get more and more degrees of freedom, which remember in chi-square it does not mean more people directly, it means more categories. In general, you have to have a larger sample size if you're trying to look at the distribution across more categories, but the degrees of freedom are not measuring the number of people directly. And as we get larger and larger number of categories, the part of the curve that is the highest point moves to the right. But all of the curves have that same positively skewed shape with a tail going out to the right. So to actually carry out our test, we calculate our observed chi-square using that equation that we saw a few slides ago. If we're working by hand, we find the critical value of chi-square for the particular degrees of freedom we had, and if our observed chi-square is larger than the critical value, so our critical value would be the value right at that dividing point. If the one that we compute is larger than that critical value, we reject the null hypothesis. When we're working in an Excel, it's instead of looking at a critical value, what Excel does is it says, there's my actual chi-square. I'm going to compute the area beyond that chi-square. So if you remember, the whole area, the part that was originally green, represented my alpha, which is usually 0.05. So the p-value is the area corresponding to my actual observed data. So if the chi-square that's observed is bigger than the critical value, the area, the part that I've colored in red, that's beyond my actual observed chi-square is going to be a smaller area than my alpha, because the alpha area was bigger, was the green one. So if my p-value is less than 0.05, I also reject the null hypothesis. So we've seen the basics of our chi-square test for the goodness of fit situation. We're going to go on and look a little bit at how the test of independence is slightly different, and then in the second video I'm going to switch to Excel and show you how the actual computations are carried out. Our second chi-square test is called a test of independence. Just like the first chi-square test, the variables are nominal or ordinal, but now I have two and sometimes more variables. My null hypothesis says they are not related to each other, or that knowing your status on one of the variables does not predict your status on the other, and that's why they're called a test of independence, because one is independent of the other. An alternate hypothesis says that the variables are related and that when I know one, it helps me predict the value on the other. And the little data set that I have here comes from the actual records of the Titanic, the ship that sank about 100 years ago in the North Atlantic. And one of the things that was widely reported was that men on the Titanic followed the rule of the day, which was to put women and children first into the lifeboats. So it's possible to look at the variables, whether you died or survived when you were on the Titanic, and whether you were male or female when you got onto the Titanic. And this is the way we usually set up our chi-square data. The 4 cells that are active are these that are in the center. This is where the actual data are. I have to add up the survived and died for males to get my total count of all the number of men there were. And the same thing for the females. If I add the died and survived, I can find out how many total women were on the ship. If I want to know the total number who survived, I have to add my survived numbers going across, and I get a total over there, and the same for died. And then I have what's called a grand total down in the lower right-hand corner. That tells me how many people were on the ship, all told. And if we look at these numbers, we can see that out of the 848 men, 680 of them died, which is quite a large proportion, compared to the 443 women, of whom 317 stayed alive. So just looking at these statistics, we get the idea that it's probably true that women were more likely than men to survive on the Titanic. But we don't have a probability value that we can associate with that, and we don't know that it's an absolutely certain fact beyond what we would expect by random chance. Our chi-square statistic is going to let us do that. The first step is going to have to be a way to compute if the null hypothesis were true, which would say that women and men were equally likely to survive on the Titanic. If that were true, how many would be in each of the categories? So let's look at that on the next slide. So here we have our same Titanic data set, but we're going to go about computing one of the expected values. When we get into Excel, we'll do a whole bunch and do the whole test all the way through. Here I want to just show you how that expected value gets computed. The equation taken straight from the textbook says that our expected value for a particular cell, in this situation I'm going to look at how many men would I expect to survive had men and women survived at the same rate. And I need to say first how many men or how many people survived, that's my row total, times the number of men, that's my column total, and then I take that multiplied number and divide by the grand total. So here I would have 45 times 848 over 1291. And this is a place where you very quickly appreciate having Excel. The numerator of this equation is 411,280. So I'd rather not be punching all of those digits into the calculator all the time. I did it once so that we'd be able to carry out this example. And the answer that I get is that the expected value was 318.57, and it went on for a few more digits, but I've rounded the digits. So a thing that you can notice is that our expected value can be a decimal or a fraction. My observed value, because it's a count of actual people, is always going to be an integer, a whole number. So my actual survivors are going to come out in numbers like 168, 172, in other words, no decimal places. But my expected values can in fact have decimal places in them. So if the null hypothesis were true, I would expect that 318.57 men would have survived if everybody had survived at the same rate, male and female. But in fact, as we see, only 168 survived. So when I go over to compute for that one cell, the part of my chi-square statistic, I'm going to take the 168, I'm going to subtract the 318.57, and you can see why we want to square it, because I'm going to get a negative number, and then I'm going to divide by that expected, which is the 318.57. When I do all those calculations all the way through, I get 71.17. It goes on for a few more digits, but that's good enough. Now remember, that was the value associated with just that one cell. The summation sign tells me I need to do the same thing for the females who survived. I need to do it for the males who died. I need to do it for the females who died. So that's why I'm going to be showing it to you in Excel. But I wanted you to see how the equation worked before we started letting the computer do most of the work for us. So the other video that's associated with chi-square is going to look at the goodness of fit test very quickly, and then carry out this Titanic data set about death and survival and gender. So if you watch the second video, you'll be able to see how the computations are carried out, and then how we reach a decision about accepting or rejecting our null hypothesis.